continue our lecture. Okay. And then we talk about Dijkstra speed up and solution of the problem. And today we will free earlier than previously because I have no a lot of time in the evening. Okay. So. About Dijkstra speed up. What is the problem that we solve for in the first part of the lecture? Finding the shortest path between all the vertices and the given vertex S. Yeah? But of course, for example, what is the application of this method? For example, if you have a transport system and you want to find the shortest path between two cities, you can use it. Yeah? Because any road has weight as time that you spend when you use that road. Yeah. Yeah. So, for example, if you search some tickets from Moscow, for example, to Berlin, for example, you want to find the shortest path between Moscow and Berlin, between 2 points. Not all the points in Moscow, yeah, not all the cities in Moscow, but between these 2 points. So another problem that we want to solve, and this it is problem to find the shortest path between two vertices, source and sink in the graph. And how we can solve this task. For example, we can start Dijkstra's algorithm, and when we add that to the set S, we can say, okay, we find shortest path between it and S, so we solve our task. Okay. But it is bad because we can find a lot of shortest paths between other vertices and S that we needn't. Yeah. So, how to speed up Dijkstra? But of course, it will be speed up in the practice, but not in the theory, because in the worst case, we get, of course, the same time complexity as we see in this table. Okay. So, for example, we can use Dijkstra algorithm and start it from the source and from the sink. Of course, using reversible edges. Yeah? And when we find vertex that will be terminated for both of the algorithm, then we say, oh, okay, that is the shortest path between source and sink. Of course, there is some problems of it. For example, we can draw this example. We have this graph, and we say that it is S and it is T. What is the shortest path between S and T? The upper path, yeah? It is the shorter. Okay. So, let's start to Dijkstra's algorithm. I write red numbers as distances from S in the forward algorithm. Yeah. and we can write these numbers. And then I write numbers, or I write green numbers as the distance from T in the reverse graph. So, when we start from S, we say that we relax all the edges that incident to S, and we set this distance equal to 3 and this distance equal to 5. And we terminate this vertex. We extract it from the queue. Then we extract this vertex from the queue of the backward algorithm. And then we relax this edge and this edge. And change these distances. 3 and 5, 2. Then we see we don't terminate these vertices. Yeah. So vertex with the minimal distance to the source, it is 3. We extract it and relax this edge. It is 3, and we extract it too.
Here, in both ways, we found common vertices.
Hmm?
Down and up. We found common vertices.
Here. But these vertices will be in both of Q's. But if you see here, when searches intersect, and it you need to understand it like when we extract from both of algorithm Q's some vertices, then we execute our algorithm and end it. Then we see that the minimal number equal to 3. We extract it and we change this equal to not 3, 6, yeah. And this of course 6 too, yeah. It was the false. Yep. Okay. Then we see we extracted these 2 vertices, and for these vertices we say that this vertex has minimal number, and we extract it. Yeah, and set this number equal to. Okay, then for green numbers, we say that we extracted these 2 vertices and minimal of these distances equal to 5. And we extract this vertex too. Yeah. When we extract one vertex from both Q's, then we terminate and say we have some vertices that have finite numbers in both arrays, yeah, in both arrays of distance. And we find minimal sum of these numbers. Of course, if we say, oh, we extract this vertex from both of Q's, yeah, and then we say 5 plus 5 is the shortest path, we will be false. So we need to compare these numbers, these sums, and say 3 plus 6 smaller than 5 plus 5, then the shortest path that will connect these vertices. Understandable? So, of course, you need to end your algorithm when you extract vertex from both of Q's, but the shortest path can not contain this vertex. We extract this vertex from both of Q's, but the shortest path between S and T doesn't contain this vertex. Understandable? Mm-hmm. Nice. So, it's about bidirectional search, and in practice, it makes smaller operation than usual Dijkstra algorithm. You can use it in the practice. Okay. And about the last algorithm for today, it's about A with star search or goal-directed search. It is another name of this algorithm. It's about similar to Dijkstra algorithm, but it has improvements and it contains important ideas, I think. About ideas. Imagine that you need to find the shortest path between this place and this place. Yeah, and of course, you will find paths that will start on the higher place and will be ends on low places. Yeah. And for example, we can set weights of these edges equal to distances, but we need to understand that there are edges that connect vertices on the same height, and there are edges that connect vertices on the other heights. Yeah, and these ideas, this idea names as a potential function that we can set for all vertices new function that we name as potential function, and we change weights for all edges from weight from U to V. We change it to new weight equal to difference between this and potential of start point plus potential function of the end point. It will be new function of weights of the edges. Okay? Why we get something interesting? Because if you can see, for example, I can draw. Yeah, I can draw some example on the board. Yeah, I set weight of this path equal to weight 1, weight 2, weight 3, yeah? It is the sum of weights on these edges. And then when we change weight of the edges and we summarize new weights, then we can say that new weights will be equal to weight of this path in the initial graph minus potential function of source plus potential function of thing. Why?
How would we know it is a function?
It is interesting because, of course, in the common way, potential function doesn't change anything. But if we have, for example, country and networks in the country, we can say that potential function equal to height of the area, for example, and we find potential function in empirical way, of course. Or for example, we know that our graph equal to two-dimensional lattice, for example, yeah. This. And then you can set some empirical ways to set different potential function in these cases. Of course, potential function you get from outside your algorithm, and in the algorithm you think that you have already had the potential function. And then you can see that it is equal to W minus some constant. And you can see that it will be equal to this, and it will be equal to this. And then we can say that we change all the weights with the same constant. So if we initially have W2 smaller than W1 smaller than W3, then we can say that this partial order will be the same for the W with overline. Understandable? Because we change with the same constant. Yeah. So, a search will be equal to Dijkstra's algorithm, and when you use weight comparison, we can see it in relax operation, we use weight in it. So here we use new weights with overline. We put here weight plus minus potential function from U plus potential function from V. Understandable? Nice. Then of course, in the worst case, we don't get speed up. And interesting that it works only if, for example, if we get bad potential function, we can not improve, but disimprove our algorithm, and it can work not quickly than Dijkstra algorithm. So you need to use it if you have empirical way to understand why your potential function is better than 0. Yeah, because if we set potential function equal to 0 for all the vertices, then we get the same graph, and then we get Dijkstra algorithm. Yeah. So of course, if you get potential function equal to distance between this vertex and sink, of course, you improve your algorithm, and it will works only O from number of vertices times, because you find the shortest path from vertex to the sink, and you find it using only number of edges in this path times your operational relaxation. And it is the optimal situation, of course, if you have potential function equal to distance to sink. But in the common way, you get different empiric potential function, and it can speed up your algorithm, but it can get more get worse algorithm than Dijkstra. Okay. So it's about a search, and that's all for today, I think. If you have any questions, tell you this question, or we can end. And of course, Masoud, Philippe, and Anda, if you have any questions, ask me. Do you have any questions about Dijkstra or Bonner-Ford algorithm, or about the shortest path problem in common way? Do you understand how to solve the shortest path problem? If we have unweighted graph, we use BFS, yeah, or we use DFS if we want, but DFS we cannot use the we need to use with understand that we cannot use it in the way to solve the shortest path problem. Yeah, only BFS.
No, we can't use D. Because DFS might give you a path that is maybe.
Because it is depth algorithm, and for example,
I can give you an example.
for example, for this graph, for example, and you want to find from the shortest path between source to sink, and DFS can find this way.
But you can find the other way.
Why? When we use DFS, we choose edge incident to vertex in the random way.
Yeah, it's not always sure that it's going to take S to T. You might get S to T of course, but it's not. It doesn't guarantee that you will get the shortest path.
Mm-hmm.
But you will get the pass.
But
it's not sure.
when we reached the first time here, like we did it, we did it like this. Can't we go back and apply it?
No, that one is like.
But no, already, yeah, because we already discovered it, yes, so.
Yes, we already discovered it.
Yeah.
So we want to run.
No,
Yeah.
yes.
So yeah, if we have random graph, we can ask if it yeah unweight, and then we use BFS. If it is weighted, yeah, if some edges is negative weight, so yeah, we use Bellman-Ford. Yes.
Yeah.
Okay. So it's all about the Schroeder space problem, and the next lesson will be about, I think, Cartesian tree, or about heaps. If you don't know about Fibonacci heap,
We will have tests, right?
about this, yeah.
Next.
No, not. I think on the 5th lecture or on the 6th lecture.
After each lecture, there is a contest.
Yeah. Of course.
No, this week we will have a new contest
And-
about.
And you need to use Bellman-Ford algorithm and Dijkstra algorithm in practice.
Yeah. Interesting.
Yeah, I wanted to ask in the
That's
previous lecture.
Hmm?
In the previous lecture.
Oh, what's
In
well?
the previous lecture.
Like the previous.
I have a question about
Oh.
ethics.
Okay.
There was something called time. I can. You don't have it.
I can open
Oh,
previous.
time. To the board. What does time do? I can see what time do, but why do we need it?
Oh, what is the slide that you
Slide
want?
number 5.
Okay.
Time. It's time when we discover the vertex.
Discover the vertex.
Yeah. Time is zero.
Here.
Time is 0. And down it's down, go right. So it's
Yeah. And here.
It's time when we discover the vertex.
Yeah.
Why do we need it?
To discover the vertex.
No, why do we need time?
Why do we need time?
Yes.
To set time when we discover and when we finish it. Of course, in the application you can use this time, and as you can see, we use it in the topological sort. Yeah, because and for finding strongly connected components. Remember it. When we use diffs, we get finish time of it, and then we repeat diffs in the graph when we reverse all the edges, and start with the vertex with the biggest number of finish time. So we use it in this way, for example. About discover time, quickly, I cannot remember any example when we use discover time, but of course you need to upgrade your time here to understand how many operations you use.
Why this? Last time, line 21. You will do F equal time.
Yeah, yeah.
What's
Finish time.
this?
It is discover time, and it is time when we finish to explore adjacent vertices to vertex U. So in the application you can use it. Because yeah, if you don't need discover time or finish time, you can drop this row from the codes. But in the common way, in the results of diffs, you get tree, diffs tree, yeah, as in the example here, yeah, you get diffs tree and get to erase discover time and finish time. And in different way you can use one first time or second time. Okay, are there in the chat, do you have any questions? No?
Question.
Okay, that's all for today.